me draw like a new, let me draw a little neural net real fast. We're gonna do we're gonna do 3 dimensions. Like if I could scroll down some more, it's not gonna let me scroll down anymore. So what if I go over here? There you go. I don't wanna confuse the pink dots. Okay, so anyway, like this is the output unit. We're gonna have this layer, and we're gonna have another layer. Yeah, and then like the inputs, and moreoverly, we're going to it's going to be like everything. I mean, like we're gonna do like a very close approximation of so we're doing like signed majority computation in the Boolean. Everything will be Boolean or binary if you prefer. And let's see. Okay, so I'll just fill this. I'm gonna fill this neural net out real fast. So these are the parameters, right? Like these are like the weight vectors, and I am picking them randomly, so it doesn't, I mean, I'm not even good at producing random bits, so like, dang man, I should have got the computer to do random bits for me. Yeah, okay. Okay, so like these are parameters. Right, so let's talk about how the neural net would run in a forward, in a normal way. And then what we're gonna do is okay, so let's do the forward pass. Yeah, I should probably, oh jeez. Oh, I know. I'll do squares for inputs, right? Yeah. Okay, so like input units don't have any parameters, right? Yeah. So okay, so anyways, we're just gonna say like we have like an arbitrary input. Let's say, let's do constant. Let's do all ones. Okay, so like this is an input. Okay, so let's do the forwards pass, just so we all understand. Cause yeah. Okay, so we're doing signed majority. So it's saying like every unit is going to be a 1 if the input vector, agrees. Oh man, my throat just went out. If the input vector agrees with the parameter vector on the majority of the indices, right? So like this one has 2 1s. This has 2 1s, so it agrees. So like that's gonna be a 1. This is gonna be a negative, right? Because it only agrees on 1 index. This is also gonna be a negative because right. So like the yellows, right? So like the yellows are the activations, and they go on top of the unit. I kind of I drew this too tight. That's fine. Okay, so we'll just keep going. So like agree, disagree, agree. So that's 2. Disagree, disagree, disagree. So that's like none. And then disagree, agree, agree. So that. And then that's the inverse of that. So we get, that's the output. Right. So that makes sense, right? Um, so what we wanted to do, not necessarily yeah, I don't think this exercise is actually helpful, but we want we want to run this backwards. So what that means is that right. So that means we're gonna fix like the we're gonna fix all the parameters. So all the greens are fixed, and then we're gonna fix the output unit, and then we're gonna run it backwards. This is not the backwards pass in gradient descent, you know, like but we're gonna run it backwards to yeah, I mean, I guess so. It's gonna be like a tree, right? Okay, so let's just try that. Okay, so do I have a pen here? Good. Let's see. Yeah, I don't. Okay. Right. So okay, so like we're saying, like if the output unit is negative, I'm going to not draw that circle. What that implies is that this layer, I think we're going to need a smaller thingy. Yeah. Right. Okay. So that's that. So what that implies is that this layer, you know, according to the parameter, ooh, yeah, see, that's going to be annoying because I chose, that's fine. What it's saying is that the input vector has to agree with the on the majority of, like, but with the negation of this, right? So that, like, this is the parameter vector. So right. So the things that agree with the majority of that are like 1 dash x, right? Like where the x doesn't matter, and you know, just 1 dash, dang man, 1x1, and x dash 1, right? So these are all possible inputs for this layer, you know, that will give you a dash. And now we're just going to keep going, although there's one more kind of, it gets slightly hairy, going further, but not too bad. So it's like, well, you know, so these are all like, well, I mean, they're just independent, I guess, possibilities. So, so let's just say we're on this branch, like, right. Yeah, okay. So then we have to say, okay, what are the, if we fix this branch in this activation, what are the possible previous layer activations that will produce this? And again, it's a function of the parameters at this layer. The parameters are fixed by assumption. Right, so like, okay, so this is saying that this unit is a 1. And so we do the same thing. You know, it's gonna be like, cool, you can have the same thing, you can have 1 x or 1 x dash, or I don't really need the ors, but I'm just writing that. X 1 dash, right? Okay, so that's for that unit. But then this unit, has its own thing. And so we're going to have to compute like an intersection between these two units, right? And like the last unit is it doesn't matter what state it is. So I don't think you have to include it in the computation. Okay, so this one is a negative for this parameter. So that means it's, 1 dash dash, and then all. I'm gonna not write the ors because that's. Oh, dang, I just deleted. Oh, dang, man. I'm like way too zoomed in. Oh, man. Okay, never mind. I'm just gonna leave that or. It's cool. Okay, 1 x dash, and then x dash dash. Right, like the x, again, it doesn't matter. Okay, so now so like these are, we can interpret these two parentheses as sets of possible possible previous layer activations. And we need to compute the set intersection. And, like we do that by, like doing all pairs, right? Because like, it's like, okay, the previous layer, maybe if it's, if it's going to give this activation, like, it has to make this one a 1, and it has to make this, so it's like an and, so it's like an intersection. Okay, so anyway, we'll just do that computation. So it's like, possibly the previous layer activation satisfies this and this, but that's not possible because the second index contradicts, right? Like, it's two different states. So that pairing is not possible. So we go here, so we have like 1x versus 1x dash, which is possible. So that's going to be 1 dash. And then, like I was going to, it'd be easier to, like write a script to do this. But, anyway, we'll just keep trucking. Alright, so we're on the first guy, and that's a contradiction. Okay. 1x dash 1 dash x, that's 1, it gives you 1 dash dash as a possible. You also retain 1x dash, because it can be 1x dash in either one. And, which kind of subsumes these two, so we can just delete the, those are gone, because they're subsumed by this. And then I'll see, 1 dash dash, also subsumed. Okay, so then going here, contradiction, 1 dash already included, and x contradiction. Okay, right. Okay, so like assuming I did that computation correctly, if our immediate previous layer is in this pattern, there's two ways to get it into that pattern, encoded by this guy, and it's like but let's just keep on this branch, right? Because like doing that computation is a huge pain in the butt. I mean, it's not entirely clear, you know. I mean, like, it's not entirely clear what the utility of this is anyway. But because like we want to do, you know, like hand program like MLPs to like represent arbitrary Boolean functions. But like that turns out to be NP hard. Like even the simplest well, yeah, I'll talk about that later. Okay, so let's just keep going down this branch. So we actually get to touch the inputs, which is good. I mean, we can see we're actually following the actual input. Like 111 is going to show up in this branch, but yeah, okay, so we'll just do the computation one more time. So we're saying this has to be a 1, so meaning 1 dash x, 1 x1, x dash 1, and then, you know, the middle one is a don't care, so we ignore it, and then this guy has to be the negation, so we're going to have 1 dash 1, and then it's going to be 1 dash x, oh, it's going to be exactly the same. Yeah. Right, no, yeah. Yeah, no, it is the same. Great. So, what does that imply? What does that imply? I mean, if you cross these, I mean, if you cross a set with itself, you just get the same set, isn't it? Okay. So, these are actually inputs at this point. So we can take this little thing and move it right here. Yeah, and then draw these guys. Right. So like that's literally right, and we can actually like let's expand these into actual inputs. Right, so you're gonna get 1 dash dash 1 dash 1 from here. 1 1 1 from here. We already have the 1 dash 1, and 1 dash 1, and then dash dash 1. So this branch represents half, you know, because we're in 3 dimensions, so there's only 8 inputs. So it represents half of all of the possible inputs. Yeah. not that, because um, I guess we could. So we just keep expanding. That's a huge pain in the butt, though. Like I don't. I don't yeah. Okay. We'll just keep expanding. I'm wondering. Yeah, that's fine. All right. I'll just keep expanding this stupid thing. All right. Okay. All right. So I mean, there's only an exponential number of other branches or whatever. All right. So we'll just go to this guy, and I'm now wondering if I mean, like, these two guys can overlap. So I don't even. Whatever. I'll just keep expanding this stupid thing. Okay. So we have two ones, and we're looking at this parameter and this parameter. So I'll just write it arbitrarily over here. So 1x, 1x dash, x, 1 dash, and then versus this guy. This is dash dash x dash x dash x dash dash. Okay, is that gonna have any intersection? No. Okay, so yeah, this is gonna have 0 intersection because all of these have a 1. Well, maybe not. I mean, this particular one has 0 intersection. This guy could match here. So that would give you 1 dash dash. And this one can only match here, and then that would give you dash 1 dash. Okay, so those are 2 branches, and we will dutifully copy them over. Oh no, I didn't draw the tree with enough room because I don't know how to do tree layout. Right. And yeah, I think dash one dash dash 1. Okay. Keep trucking. Keep trucking. All right. So we got 1. Yeah. I mean, like these 2 things overlap. I don't know how to interpret that. Anyway, okay, so like, is that gonna happen? There's 1 dash. Well, I mean, it could, because, I mean, like this, like these two thingies overlap 1-1, and yeah, okay, well, I'll just, I'll just keep expanding this guy. Oh, that one's gonna be hard to expand because it's three-way. Well, I mean, it's going to be the same here, except yeah, it'd be the same here, except this one would have to be like a dash. I don't know if that's actually true, but since I don't want to expand a three-way, I should write a script to do that. Right, so we're just going to say that necessarily gives you this. And maybe it doesn't, though. Because, I mean, I guess you could have, like, because, I mean, what that says is, like, for instance, this input, it, you know, it can, I guess, like, it, like, it's overdetermined, like, it, it makes the output negative for two reasons, at least, because, like, it goes through this branch, and also goes through this branch. Yeah, I think it would just be easier to script this. I mean, I don't think it's not really clear that's going to help with interpretability in any way, because it might, though. And well, yeah. I mean, that'd be a pain in the butt to script, though. Because, like, you have to have the, store the parameters. You have to store all the parameters, and then given an activation for a parameter, you have to produce all of the ORs. And then, like, yeah, I mean, we could just do those as strings, though. And then we could just do literal, could you just do literal set intersection? I don't think you can, because no, I mean, well, you could if you don't have the x's. If you just, like, literally expand, right? So this 1 dash would be 1-1, also 1 dash dash. Yeah, but no, I think the x's help with interpretability. Yeah, so you'd have to do like explicit intersection, and then you'd have to like build it into a tree, and then you'd have to visualize the tree. Yeah. That seems very hard to implement. Let's try to script it. I mean, I don't think it's, I mean, it's not gonna, right, because, yeah, alright. Okay, let's just try to script this. Okay, so we're given all of the greens. Those are the parameters. Also called weights. And also just implicitly, all of our biases are 0. So, we just don't have them. You could though. You could. I mean, that's kind of like an open question. You know, like, open question, are there Boolean functions that, if you're using this pseudo MLP, like signed majority, layered composition circuit, do there exist Boolean functions where, you know, like the smallest circuit that computes it with, if you don't have biases, is exponentially larger than, or, you know, like what's the blow up inefficiency with if you have biases versus not? Don't know. Okay, yeah, I'm gonna try to script this, although like it's very painful. It's like exceedingly painful. I'm gonna try to do it like in pseudocodes. Okay, so we have the green. Okay, so first of all, we have to talk about like the representation of the neural net. Yeah, I mean, I think you just represent that as an array. Yeah. Right. So neural net, and then this is, you know, right. First layer, second layer, last layer, and then the first layer will have, in this case, 3 units. The second layer has 3 units, and the last layer has 1 unit. You know, and then you just like fill them out, like 1, -1, 1, so forth. Yeah. Okay, so that's right. So we're trying to convert this into a tree. I mean, I know like you can use, I mean, like if we're using Python, you can use various tree libraries, or like graph visualization libraries. Yeah, so right, so like we're going backwards, so Okay, so I think, seems like you want to do something like 4, 4-layer going backwards. So like, if we call this neural net, so yeah, you just go backwards. Yeah, so like you start at length of neural net -1, and you go to however that works, 0, whatever. Great. Okay, then you have to, yeah, you're gonna have to, for every unit, expand, right? Because like so you need to expand the sign majority into these possible states. And yeah, I guess we're allowing that like the states can overlap, because I mean, like, if you yeah, I mean, I think that's possibly like a useful part of the interpretation. Because, I mean, you could collapse everything to just raw activations where you don't have the X variable. But yeah, but we're just going to keep that. So, also right, dang man. Well, still recursively. Yeah. Right? I mean, that's a tree, so it should be recursive. Okay. Yeah. Right. Okay. So it's gonna be like expand node. Although I'm not gonna write out node. And I think you're going to need to know what layer you're in, because you have to index into the neural net. Or, I mean, like, could you, I guess like you could, like, could you pop the neural net and then pass it to the children? Would that be cool? Yeah, that'd be very cool. Okay. So I'll just pass in the neural net, and right, I mean, it'd be like, it'd be like you're here. Right, like if you're expanding this, yeah, yeah, so like parent, you need parent activation. Right? I don't know, this is not going very well. I don't like trees. Okay, so think about like expanding this one. Okay, so So like your params are going to be some variant of pop. Like, I mean, you're assuming we're, although also we need to make, like, I mean, every branch needs to have its own copy. So, yeah. But anyway, then you pop off the back. Right. And then, yeah. And then, yeah, we're just gonna have, like, params. So then you're gonna have, you gotta compute, right, so you'll have, child activation, which will be the branch. It's like a set structure. And then, you're just gonna walk through, you're gonna, okay. I mean, like, each unit, you have to produce the possible variables, possible joint activations for the previous layer. Yeah, then you have to do always, god damn it, man.